guys think about 170 minus 17. And I want to build both of those. So whose strategy is better? Well, I don't really want to say it that way. What I want to say to students is, which one do you wish you would do? Which one do you wish your brain more naturally was inclined to do the next time you run into 9 times 17? You know, when you're walking down the street and you run into 9 times 17 and you have to solve it? Which way do you... What do you carry with you? Do you carry 1 bag of Skittles and 8 bags of Skittles to get the 9, or do you tend to carry 10 bags of Skittles? Which sort of lives in your brain?
10.
9 times 17 or 10? Or 8, excuse me. Does 8 times 17 live in your brain, or 10 times 17? 10 times 17 tends to be the one that we can access a little bit easier, so I might not want to walk like an Egyptian in this case. I might want to use the 10 times 17. All right, but again, what I didn't just do was dog this gentleman's strategy. What I did say was excellent, because I modeled it, I celebrated it, I model, and then I say, which one might I carry with me? What might be more efficient for me to do a little bit later? All right, the next problem in this problem string is I might ask you for 5 bags of Skittles. Let me make sure enough of it is on there. So how many Skittles would be in 5 bags? And if we had a little bit more time, we would share some more strategies. Notice that I clean this up as I go. I don't like to do these problem strings on chart paper, or what's another way I can't erase? I don't like to do it in such a way that I cannot erase, because I want to be able to model someone's strategy and then clean it up so I can continue to model as I go. So 5 bags of Skittles? Well, okay, so we're running out of time, so I'm going to run through really quickly. Could I add 1 and 4? Could I think like an Egyptian and add 1 and 4 to get the 5? I could. But could I also half 10?
Yes.
Yeah.
Could I half 10 bags? What is half of 170? Indeed, that is 85. Now, I might model that in a couple different ways. Could I think about half of 170? Middle school teachers, watch this. 5th grade now. Could I think about half of 170 by half of 160? And half of 10 more? Is that a half of 170? What else could I do?
Half of 100.
Half of 100, that's not the one I was going to do, but I'll do it anyway. Half of 100 and half of 70. One more. Okay, the one I was thinking of. How about a half of 180? And then what? Now I have to subtract half of 10. Okay, so when our standards call for us to make connections between division and fractions, here's a way to do it. It's not the only, but it's a way to do it. Connecting division and fractions. So when you see that crazy standard that has a divided by b equals a over b, this is a way to meet that standard, 5th grade teachers. A way. Meaning I want to do more. See, right? I don't want to be sparse. I don't want to have this be the only way. I'm looking at a new 5th grade teacher over there. All right, raise your hand. This is an old student of mine at UT, and she came to introduce herself. Yay! You have people that are going into education. Have them come to UT and take my class. Wouldn't we have? Okay. All right. We have lots of fun. Why? We want to build it from the get-go, right? We're all these elementary teachers, and then as a secondary teacher, we can just take them from where they are and go. That'd be great. Well, we know we don't have that right now, so I suggest that you build their numeracy and the math that you're supposed to teach at the same time. All right, so we just did 5 bags of Skittles. What if I asked you for 100 bags of Skittles? And I used to add 2 zeros. No, I still want to be talking multiplicative relationships, so I want not 117s. Now I want to think about 17 100s. So I'm going to multiply 100 here, I'm going to multiply by 100 here. 17 100s, hey, 1700s, what does that look like? Doesn't that look like 1700? Absolutely, that's a good thing. All right, so if we know that there's 1700 and 100 bags, how about 99 bags of Skittles? Don't say it out loud. Everybody thinking? We had 17 in 1 bag. Now I want 99. How many Skittles are in 99 bags? Did many of you think about 100 bags and 1 bag? Can you see that?
Yeah.
Because 100 bags minus 1 bag is 99 bags. So the corresponding Skittles in 100 bags minus the Skittles in 1 bag, what is 1700? Subtract 17. Oh, now we gotta line those up, right? A little across the outies and stuff. Or can you think about the relationship between 1700 and 17? What is 17? How might I think about 1700 minus 17? What's one way? I can subtract 10. What is that? 1690, and then I still have 7 left. What's 1690 minus 7? 1683. Andy, will you remind me in about 10 minutes to do I have, you, need? You can just write down I have, you, need. Thank you. Okay, so do I have 1683 in 99 bags?
Yes.
Absolutely. What do you think? Yeah? And we just did 99 times 17 in about 3 mental steps. Now you might say mental, Pam, you wrote stuff down. Mental does not mean that it's all in your head. Mental means that you did it with your head, that it was your thinking, the relationships that you own. So I want you to keep track of your mental steps if you need to. I want you to write down and model your thinking so that your students can see what you're thinking. That's a necessary thing. Mental math does not mean that it's all in your head. Mental math means that you do it with your head. So then I might ask you, if I know that I have 1683 Skittles in 99, I wonder how many, I've been giving you numbers of bags, and you've been telling me Skittles. I'm going to tell you that right now I have 255 Skittles. How many bags do I have? I have 255 Skittles. How many bags do I have? Now, what were you thinking? Now, unfortunately, if I was in a real workshop and I had lots of time, I would have given you more time. So if you're me and you're still thinking, sorry, it's okay. It's okay. Go home and think about 255 Skittles. What could we think about? What did many of you start doing? Did many of you start looking around here?
Yes.
What's that near? Well, what is it near? What's it close to? Well, let's see. We have, I don't know, we have 170. And we have 85. What is 170 and 85? That happens to be 255. Now that might have taken you more time than I just gave you. That's okay. But if 170 and 85, if I add those together, then I need to add the corresponding bags together, then it should be 15 bags. And what problem did we just, before we had solved 99 times 17 in 3 nice mental steps, what did we just solve this time? 255 divided by 17? Yeah, baby, long division. Thinking and reasoning. Now you might say, yeah, but Pam, how would a kid solve that if we didn't have all that? Let's do one more. Like if we didn't have all this stuff up there, do we really want kids doing all this to solve that one problem? Heavens no, but we wouldn't need to. Let me give you one more example and then we'll talk about what a kid might do. What if I were to ask you for 1,666 Skittles, how many bags? 1,666 Skittles, how many bags? Where are you looking? So you're looking up here and you're thinking, well, what is it near? I bet some of you, did anybody use the 1683? Yeah? Because is that kind of close?
Yes.
How close is it?
Super.
Super. How close? Well, it happens to be 17 close, right? Are those 17 apart? Hey, they're one bag apart. So what is 99 subtract, this is hard, one bag? Is that 98 bags? Nice! I bet some of you didn't use the 1683. And you're like, what else would you have used? Did anybody use the 1700? Well, how close is 1700? How close is 1700 to 1666? 34. Hey, we happen to have 34 up in our table. Check it out. There's 34. How many bags is that? 2 bags. What's 100? That 100 bags subtract the 2 bags, and we're back to the 98. Yeah? So what I want to just suggest is what problem did we just solve? If it was 1666. Did we just solve 1666 divided by 17? So you might say to me, yeah, that's because all that stuff was up there. And I'm here to suggest, now, if you build this kind of numeracy in students, then the student might approach this problem, written that way or this way. They might approach that using some thinking. Like, they might say to themselves, what do I know about 17s? Well, let's see, if I have a bag of Skittles that has 17 Skittles in it, 17, how close can I get to this 1666? Hey, 117s, that's 1700, that's kind of close. How close is it? Now I ask the question how close it is. 1700 minus 666, oh, that's just 34. How does that 34 relate to the 17? It's just 2 of them. And you're done. So really, we don't need all that other stuff. We just need kids thinking and reasoning about how close that is. Notice how many steps we just did to do this 2-digit into 4-digit division, long division. I want you to think about what a kid might have to do if they were doing this problem in a traditional manner. So looking over here, 17 goes into 1. So, right? We're over here. 17 goes into 16. 17 goes into 166. And the kid looks at you and goes, I'm sure it does. And then they go off on the side of their paper and they do 17 times everything and they get half of it wrong, right? That's not thinking and reasoning. That's trying to memorize somebody else's mathematics. So I want them thinking. Now, here's another problem, middle school teachers. If we teach the standard long division algorithm the way we have in the past, and kids say 17 goes into 1, ask 17 goes into 1 a slightly more mathematical way, instead of saying gazetta. Aren't we asking 17 times what is 1? Isn't that another way of saying 17 goes into 1? So when you say 17 goes into 1, that doesn't work, I better move on. Are you really saying that there's nothing 17 times to get 1? What is 17 times what is 1? 117. Can you do that? We're working against ourselves. When we teach kids to long divide by using the long division algorithm, that's it, they memorize it, we are working against fraction understanding. We're working against rational number understanding because we're sort of suggesting that there's nothing times 17 that equals 1. Oh, yes, there is. And it's 1/17th. And that's an important number. That's an important concept. So I'm a little against using the standard algorithms to teach as the only way. We have to teach the standard algorithms because every standard calls for that. Every set of standards across the nation calls for teaching the standard algorithms. My suggestion is that you teach thinking and reasoning about problems first, and then you study how the algorithms work. Because it is a fascinating study in place value, but not as your strategy of choice. Because a kid will study how it works and go, wow, that is intense. Who came up with that? Because that is really, they like stuck a lot of meaning behind the scenes. You can't really tell what's going on because all that place value is like embedded in there. And whoa, why would anyone ever do that if you could just think about the numbers? Because you've already taught them to just think about the numbers, yeah? Okay, so I can do the exact same kind of thing with decimals.